Okay. Okay, so hope everyone's well. Today I will be talking about um, last time we defined what message integrity is, MACs, and we showed that a PRF implies a MAC for a small message space, right? That in order to create a MAC, you just compute a PRF on the input, and the output is to the random string. So having seen PRF outputs on any number of messages, you cannot predict what a PRF output on a new message would be. Therefore, it's an unforgeable MAC. But that works only on the message space that is the same as the inputs of a PRF. So how do we extend this? And this is also practical MAC concept. Okay. Many are basically PRFs on a large input domain. So here is this simple MAC to a PRF. And so using AES, whose input domain is 128 bits, which is 16 bytes, you can MAC a 16-byte message this way. 16 bytes is not that much, right? So of course, you want to somehow go from this MAC on a small message to a MAC on a large one. And these are the two constructions we'll show in a sec. CBC MAC and NMAC. They're both part of. They both operate in the real world, and we'll see how they work. So here is the first of them. It's a CBC MAC. You can see that its circuitry is very similar to CBC encryption. If F is a block cipher, then you take your message, you divide it into blocks whose size is the same as the plain text block of the block cipher. So in the case of AES, these are 16-byte chunks of the message. And then you put them through the CBC. However, CBC encryption first chose a random IV and masked the first block of the plain text with this IV. Here we don't do that. That's the first difference. And you take the resulting cipher that comes out from using the block cipher, and you use it as in CBC, cipher block chaining. To chain, you use the cipher that comes out here to chain the next ones. How? As a mask with which you XOR the next block. You take that masked block number 1 into the block cipher. You look at the cipher now, and you use it as a mask for the next one. And so you go exactly like in CBC encryption, but you take this last output and then you post-process it. So you actually have, this is all done with a single key, just like in CBC encryption. But when you output the ciphertext, you post-process it with the same block cipher, same F, same PRF, but a new random key. In fact, the encrypted CBC, the key space is a pair of keys of F. So if F's key space is K, the ECBC using this block cipher F, its key space would be K squared. So a pair of two values in space K. This is one, this is the other. The message space of the encrypted CBC is any number of blocks. So if these are 16 bytes for the case of AES, these are any sequences of 16 bytes up to some limit. So as in the case of encryption construction, modes of operation of the block cipher, we'll say, okay, there is some polynomial in security parameter, capital L. It's the limit of the size of the message that you can put through this. And this whole thing defines key function, right, whose keys is the third, on what domain any strings containing at most L items from domain X. This is the new domain of this new function. And the claim is that this is a PRF. With these type of pair keys were pairs, and the domain were sequences of arbitrary length of chunks of X up to element L. The range of the PRF is X itself, because this last block cipher is associated with DK1, outputs the cipher also in X, right? Because the range of F is X. So that's the range of this whole construction. This post-processing with a new key, let's first look at this construction without this post-processing. So let's look at this, everything in the green region. We call that a raw CBC or a basic CBC. And if you add this post-processing, we call this whole thing an encrypted CBC, because you can think of this wire as an output of the CBC. You chain, you run this cipher with key K, chaining the block ciphers in this way. You recurse, it's the same operation, right? You can do it in place in software. Take blocks, output, take the next block, XOR it with the next one, and go through. XOR with the next one, go through. You output something at the end. That's this wire. And what this does is conceptually it encrypts this wire, because here F is assumed to be a block cipher, so it assumes to be going in both directions. It's a what is it called? The code book encryption, right? So an encryption of this wire is just the block cipher put through it. So what's this underlying green thing? So we'll start with this in a bit, okay? You might observe some differences from standard CBC, the CBC encryption. What are they? As we said here, that you're not picking any IV, you're not masking the first block. And a second difference is that in a CBC encryption, you release all these intermediary wires as blocks of the cipher, right? The encryption is the first of all the IV, which in some sense is like an all-zero string here, and the outputs, these intermediary wires, right? These form the ciphertext. Indeed, without these intermediary wires, you cannot decrypt, right? It's only if you know these two wires, you can compute this block cipher backward, XOR, and get the block. But our purpose here is not encryption. We don't care if there is some way to go from the MAC back to the message. No. What the functionality that the MAC has to support is ability to go forward, compute the tags, and then to verify them. But because this will be, the claim is that this whole thing implements a PRF. So therefore, MACing is still going to be like this basic MAC idea on this slide. You take your message and you apply this PRF to this message. This PRF is this complicated encrypted CBC MAC construction, but it is still a PRF, and the MAC is just its output. To verify, you take a key and the message itself, and you compute the PRF forward, and that's the only way you know how to, and you compare against the tag, right? So that's why you don't have to show these values. In fact, if you do show them, then as a MAC, this would not be secure. That is one of the exercises to see what happens in this construction. Here is the alternative. This is not the only way to chain. If you try to come up with a MAC based on a counter mode or an OFB, it's not going to be clear how to, because those modes took some IV, expanded it, either counter mode or OFB, into a long string, and then what they did with the message was the plain XOR. Now, that is not going to protect integrity of the message, right? Because XOR is XOR homomorphic. Okay, you say that this is a microphone issue. Okay. Oh, I'm so sorry. So somebody said that before. How about this one? Does it get any better when I when I speak without these headphones? Okay, I see. These are the second headphones. And students reported that the first one had static, and now this one doesn't sound very good either. Okay. All right. Well, hopefully this microphone is not too bad. Thank you. And I didn't have this open, so I have to keep the chat open. Okay. Okay. What is the alternative way? Here's the nested MAC. So, okay, what I was saying is that if you try to do counter mode or OFB, output feedback, it's not really how to convert them to a MAC, because what they do with the message is just an XOR of this, essentially a PRG string with the message. So that is XOR malleable, right? You XOR with any delta, and you get the correct construction. Correct output of the same function applied to a message modified as the original message XORed with any delta shift that adversary wants to use. But here is something that is okay, that looks really different from an encryption from using block cipher for encryption purposes. So I use a block cipher on the first message with the key. I take the output and I use it as a key in the next application of the block cipher. So here, the cipher that came out of here is used as a key in the next application of the block cipher. This is the plain text block. I encrypt, excuse me, sorry about that. I encrypt M1 under this key, get another cipher block, and I use this as a key for the next application. Okay. So now syntactically, F have to be have different domain and range. Indeed, I need a PRF whose range is the key space. So it maps plain text block into element of a key space. Now, note that in AES, the basic one is 128 bits. The keys and the plain text blocks are the same size. So basically K equal X for AES 128. For DES, well, the basic DES had the key was 56 bits and the plain text was 64.
So you just output 64 bits and you cut them. You take the 54 out of 64. Yeah, 56, right? You just cut the 8 bits. Now, hold on a second. There's noises. Hold on a second. Oh, I see. Okay, yeah. Oh. No, okay, thank you. Sorry about that. So, so you can do this for both AES and DES, right? If you want to do triple DES, it's not so clear. Or AES 256, where the keys are twice longer than the plain text block. So what do you do? Well, you have to work a little bit. You have to basically create a domain range extension for the PRF, but that can be done. So if you think of a tree-based construction of the PRF to begin with, you can see that if you want to extend the range, you can do so. Actually, the very basic one is you apply any PRG to the output of a PRF, and that extends the range. So a new PRF defined, take a PRF and then take an output and extend it with a PRG. That's also a PRF. Okay. All right. So you do this. It's called cascade. This usage of when the output of the previous instance is uses a key in the next instance. And so you have this final output. Typically, this is smaller. The keys here are smaller than the plaintext block. So that wasn't for the case of DES. So you post pad it with some fixed pad, and again run it once more. This post processing is an encryption. It's exactly like in the case of a CBC, encrypted CBC. I take the output and I encrypt it under an independent key K1. I do this right here as well. All right, except that because for the case of DES, T is only 56-bit long and I need 64 bits here, I use some fixed padding to patch up. Okay, so the two constructions have this similarity of the post-processing of encryption with an independent key. By the way, so here my key is longer. Does it have to be? Not really, because you can use an EPRG to extend a 128-bit key into a 256 one, right? So, your keys don't really have to be longer, right? But it's easier to think of them as a pair. So, cascade is easier to see why you need this post-processing. So imagine that just like in the case of the encrypted CBC, this is called well, like a raw nested MAC, but it also has its specific name, cascade. Why don't we end here? Why don't we just call T the MAC? And the issue is this, that this is not easy to see, that cascade can be extended. So if I see one output of the cascade on some message, then I can locally take the output of the cascade for a given key on a message, and without knowing the key, I can locally take this tag and extend it into a correct output of the cascade construction with the same unknown to me, key K, on the original message, extended by any postfix. Let's see why that is. So let's say that the original message had only 2 blocks, M0 and M1. And if the MAC is write this value, then if I ran this construction with the message M0 and M1, I mean, the message whose only 2 blocks are these first 2 blocks, then the MAC would be this wire, right? Because the construction is deterministic. So it always starts with the same key K and would process it like this, and this would be the MAC. So that would be a MAC that an attacker would get. That would be the MAC on this message, the two first blocks. And now look, given this wire, an attacker can run this construction forward now on any M3 and get this wire. And what is this wire? This is a MAC on M0, M1, M3. You know, oh, sorry, this is a stupid numbering. I just noticed that I had a typo here, right? These are supposed to be consecutive blocks of the same message, and now I see that I have a skip. I don't have a block number 2. But if the correct MAC on a message that contains 3 blocks now, the M0, M1, the original blocks of message M, followed by the third block M3, the MAC on that would be this wire. And attacker can compute this wire because from this one, a MAC on M0, M1, and this one, he just runs the block cipher forwards and he gets this value. So that's a forgery. Also, attacker can continue. And that he can do it for any M3, right? And also for any M4. So that's why this cascade has this extensibility. If you give me the intermediary wire that is an output of a cascade on some number of blocks, then without knowing the key, just using this intermediary wire, I can continue this construction on the original message, followed by arbitrary blocks of my choice. And I can continue computing it by myself without knowing the key. So that will be an immediate attack on the MAC, right? Because the attacker says, please sign M, the challenger signs it. And then the attacker can forge MACs on M followed by anything. So that's, yes. So the raw construction is insecure. However, raw construction limited to any particular number of rounds is secure. So if all you're doing is you're smacking fixed number of blocks, so messages, not rounds, blocks. If you're only marking rather than general sequences of length up to L, you're marking only exactly sequences of L, then the extension attack does not work, right? Because I can only submit L blocks to be marked, and on anything longer than L blocks, MAC is going to fail because it only says, okay, I have this fixed length L that I'm going to work on. And so the same will be in the verification process. That doesn't yet say, why it is secure, but this cascade sensor is secure for this fixed sequence length. And it's an interesting thing that this post-processing actually it's enough of a separator. So from the results that shows that if on a fixed length it is secure, the fact that I'm post-processing using encryption, no matter what is inside here, if what I have here is a family of MACs who compute correctly, no, sorry. No, that's not true. What I was going to say, that this works in general, does not matter. And word construction, no, that is not true. And so I need does not suffice that it works for fixed messages. Okay. So now the same attack also can apply to CBC. Okay, rather, it's a similar attack. So the CBC, if you run a raw CBC, okay, so in other words, a MAC on, say, this message that's composed of these two blocks was this wire without the post-processing of encryption, then you could extend this and okay, except that is not so immediate as in the case of cascade, because even if you know this wire, then let's say you want to extend this message. So you apply M3, you know this XOR, but you cannot really compute this, right? Because you don't have key K. In the case of cascade, this block cipher used this wire as a key, but this guy uses the secret key to which the attacker does not have an access. And nevertheless, basically, what you use is that you see FK in operation in previous rounds. And even though you cannot compute FK on anything that of your, that you want, like you already have seen FK operating on some wires, and that suffices to basically fix this wire in a way that will reconstruct some values that already appeared here before. And therefore, the output will also be predictable to the attacker. So the attack is more complicated than in case of cascade, but not much more. Okay, and you can reconstruct it. Okay, so the analysis of both CBC MAC, encrypted CBC MAC, and the NMAC is that these are PRFs if the underlying F is a PRF. So exactly, if you have a PRF attacker on either the encrypted CBC or on NMAC as PRFs, so he submits any messages of arbitrary length, these orange blocks, and he gets back a tag on them. And he now sends another message, maybe shorter, maybe longer, gets a tag on that. He cannot tell interaction with such a box on fixed but chosen randomly at the beginning keeper K1 from interaction with a random box, a random function, which on arbitrary strings just picks this tag output at random. And the only consistency it has is that if you query it twice on the exact same string, you get the exact same value. Otherwise, these values are picked at random every time. So if F is a PRF, then you cannot tell interaction with this construction from a random function. And the exact statements are that the advantage against the encrypted CBC MAC is upper bounded by the difference from looking at the block cipher as a pseudorandom permutation. So in a sense, in the first step of the analysis, you replace all the little PRFs with ideal block ciphers with ideal pseudorandom permutation, true random permutation. And then you argue combinatorially that you no longer have, cryptographic components. You have a perfect random permutation. That the only way you can see, you can correlate outputs here with anything. You can find any correlation is if there is going to be some repeats. This analysis, if you replace FK with a true random permutation, then you can see that the only things that can go wrong is if you create a collision. So this wire appears twice for two different messages, and you can coordinate like that. This appearing twice results in well, it cannot happen, or it can happen only with negligible probability unless you have some other forms of collision on the previous wires. This type of thinking turns out you can do this analysis. The probability of these bad events, of some forms of collisions on these wires, is upper bounded by the number of queries square over the domain range, and it is not related to length of L. Here, though, with the NMAC, it is, and quite strongly, right? So the advantage against the PRF, we cannot do such a sort of easy change intuitively, because the PRF in an NMAC, nested MAC, executes on a different key every time. So we cannot make a reduction against a single PRF instance. Every time it's used, it's really a different instance of the underlying PRF. So it's as many queries, and with really every block of the message, that the initial key used is always the same. But if you have 100 block message, then the 99 of these keys will be fresh. And for every query, these keys are output of the first block. So again, they can be all independent, right? Because if the block is different on the first block in all these Q queries is different, then the second key is already, these are already new instances of the PRF. So the reduction is more complex, and also typically key space is smaller than a space of X, right? Like for example, for DES. So okay, but let's say that if you take triple DES, then now a nested MAC will be better, right? So it's here is a big jump between using triple DES in this. So for AES, both of these terms are the same, right? Because it's 2 to the 128 in both cases. So you take square root of that, it's the same, 2 to the 64. For triple DES, it's a huge difference. This is 64 bits, so its square root is 2 to the 32, and this is it's 168, right? 3 times 56. And so half of that is 84, right? So these bounds perform very, very differently, and you get a very good bound for nested MAC essentially with triple DES. So they are the encrypted CBC MAC is used in 802.11, the wireless encryption. It's a NIST standard. It's called CMAC, so cipher MAC. But an NMAC is it has a bottleneck in that for every new block you are using the encryption on a new key, right? So in here you're switching a key every time. Block ciphers are not optimized for this use, because what the block cipher is going to do with a key is to first expand it into using a PRG to create different round keys, right? And then run the inner round functions using this expanded key. The expansion is very often at least as expensive as the block cipher itself, often more. So that is going to perform much worse than this one, where the key is the same in every instance. So okay, here is one clue why you might want to do an NMAC instead, right? For some key spaces, you're gaining security, but what do you do with this fact that you are you need a new key for every block? We'll come back to it, because it's the security analysis of this is gave us reasons, extends to security analysis of a very standard popular MAC scheme called HMAC, for like hashed MAC. And basically HMAC can be seen as an instance of this for a particular block cipher for which changing the key actually is not going to be so costly. And once you instantiate things this way, then you see that there is a hardware on which this can run very fast. One more thing about this is that these security bounds, which, well, as I was saying, these are because of the reductions, right? But these bounds are combinatorial in arguments, and you can ask, okay, you can make this combinatorial. This is a bad event that messes up your security analysis, or rather helps the attacker. But can you improve these bounds? Perhaps this is an event that helps the attacker, but you have bounded it liberally, and you can make these bounds tighter. So no, the bounds are exact. So there's actually explicit attacks that if the number of queries reaches square root of the domain size, So 2 to the 64 for AES, 2 to the 32 for DES, or key space in the case of the nested MAC, then there is actually an attack. Okay, so both of these PRFs have the following extension property, that if you, which is different from the attack on the cascade, although it looks very similar, but it's actually a different thing. The extension property is the following, that if this big domain PRF, either encrypted CBC or NMAC, for any key, if you find two messages, X and Y, on which this PRF collides, so perhaps X has 5 blocks, right, and it's processed through ECBC, and perhaps Y has 15 blocks, but when it's processed through ECBC, there is a collision. Okay, then there is an immediate attack on the MAC. If you find a collision in this PRF, then you find an attack against the MAC. Why? Because of the following extension property, that if X and Y, however long messages these are, they create a collision, then any two pair of messages formed as the same X and Y followed by some number of blocks W, and it's the same blocks that I that I append to X, and I also take the same blocks and I append them to Y. If I put these two messages through the same big PRF, I'm guaranteed to get a collision as well. Why is that? Okay, so this you can observe by just looking at the so I have a reference for this attack? Somebody says here is an attack. Okay, so let me get let's see first why this is true. Okay, why this extensibility is true. So let's look at the circuitry here, right? Let's say you have two orange messages, this one and some message M prime. Let's say they all have 4 blocks, okay, but that doesn't actually is not needed for the argument. And let's say that the tag is the same on these two messages. Well, if the tag is the same, then it must be that also this wire was the same, right? Because it's deterministic, and I use K1 in both cases. So this wire was the same. So therefore, this wire was the same in both constructions. And now think, what do these two circuitry do if I run? So I have these two messages, M and M prime. And now I run the circuitry on message M followed by W and also M prime followed by W. Okay, let's say now that M and M prime had just 2 blocks. So it's this wire that was the same when I ran it on M0, M1 and M prime 0 and M prime 1. This wire was collided in these two executions. Then if I followed by the same W, then the collisions would carry on because it's deterministic. So when I ran it on M message and I ran it on M prime and this wire collided, if I follow M with any postfix and M prime with any postfix, I would encounter collisions in all the other wires. because it's deterministic. It's the same here. If I had a collision in the final tag, this is deterministic. So therefore, I must have a collision in here. If this was a PRP, right? Which means that it cannot, two different inputs cannot have two different outputs. The only way you can make this output the same if its input was the same. And so if this input was the same, now if I postfixed with any further blocks, then any further down, now just collisions will just continue, right? Because this circuitry is deterministic function of whatever this wire is and the blocks I'm going to append. So it will collide from then on. This is why this property holds for both constructions. And so now what is the attack? The attack is just sample X and Y at random. So just if the, let's say in general, I denote the output range of this big PRF with capital Y. It is X in the case of CBC MAC, and it's K in this case of NMAC, but in general it's just some capital Y. So I sample so many messages, and I ran them through the I asked them to be MAC'd. So this PRF is executes on so many different MIs. If this is even a perfect PRF, so it acts like a random function, these TIs are random samples from the range. So after I see so many samples from this range, by birthday paradox, right? I have a probability of finding a collision with high probability when I reach this bound. So at that point, I have some two messages, MU and MV, such that the messages differ, but TU and TV are the same. It's a collision on this big PRF. So now I can ask for a MAC on MU followed by anything, and I output forgery MV followed by the same thing with the same MAC, and it's guaranteed to work, right? So these bounds are necessary, and indeed getting MACs which break through the birthday probability barrier is not obvious, and this birthday probability barrier is significant for some constructions that you want to, even for AES. 2 to the 64 is not an unimaginably large number, so we would like to get constructions which are secure against larger bounds, for larger bounds. Okay. So, and this is something I mentioned before, that if I run, actually in the case of NMAC, but the same is true for CBC. If I run CBC on fixed length messages, however long, but always the same, then it is then I don't have to do post-processing encryption. So raw CBC works, and the same for NMAC. And this final encryption move that takes raw CBC output and encrypts it, it separates the lengths. So the way this construction works on messages of different length, and I cannot now play games with length, and that is how the security for these things is argued. Some things that became were so. I'm not giving you the perfect argument. I'm giving you some attacks and security. You know how the argument works. I'm sketching the main arguments at this point. In encryption, padding was not so much an issue if the way I encrypt arbitrary size message, even if it doesn't fit into block size, well, I pad with some all zeros if my message ends, you know, not on the block size boundary. And I just discard them. The receiver will discard these extra bits. But for message integrity, these arbitrary paddings are going to be an issue because as you will see in a second. So let's say you're doing encrypted CBC and the message didn't end at the block boundary. What do you use here? If okay, so that's a question I can pose to you. If the way I marked was that I performed a PRF, this MAC construction, on a message extended with a bunch of zeros, the receiver gets the light orange message and he extends it with a bunch of zeros to the exact block size and performs the PRF on it, compares with the result, so the receiver can do it. Now, but is this a secure MAC? So again, the question is, if I assumed on previous slides that my messages were always multiples of a block size. Let's say now I want to encrypt arbitrary bit strings, in particular bit strings that don't end at the block size boundary. And so what can I do? How about filling up the rest of the block with an all zero string? So somebody says that it should depend. Any other guesses? So no, so exactly. So this is the attack. Because if you are given a tag on message M, right, PRF applied to M, it's really a PRF applied to M extended with a bunch of zeros. So the PRF on M extended with just 1 0 is the same, because if you took this message and this also doesn't end at the block boundary, right? I needed 4 more bits, and using this I got just 1 more bit, so I still need 3 bits. And what I'm going to do, I'm going to fill the other 3 bits with zeros. So this message padded is the same as this message padded. So my padding collided this message with this one. The input to the PRF was the same if I mapped this message and this message. And so it is forgeable. Because let's say attacker asks the application to map M, and it forges because the same MAC also works correctly on M followed by a 0. In many applications, adding extra zeros to a message perhaps is not going to really constitute any attack, but in other applications it might, right? I mean, if a bit string is interpreted as an integer, if I add a zeros at the end, it depends whether I encode which side I encode, but it might be equivalent to multiplying a number by a factor of 2. So I don't want, like if I send a message, please transfer $10 to my friend's account, I don't want him to be able to multiply it by a bunch of factors of 2 and obtain a valid MAC on the resulting message. So I need some encoding which will not create collisions of this sort. So basically, it's an invertible encoding, right? That two different messages cannot create the same padded message. So here is the invertible encoding that is used all over in in computer practice. It's sorry. Sorry about that. Okay. It is I pad by putting a 1 and then filling up with zeros. So now to decode, it is a so-called unambiguous encoding, right? Because given a result, I just go from the end and I go like this. The minute I encounter a 1, I stop, cut it out, and the rest is the message. And this is unambiguous because whenever I start, there will be a 1, right? At some point. This encoding is not. It is not non-ambiguous, right? So it is an ambiguity. When I decode, I do not know whether these zeros were part of the message or they were part of encoding. If, on the other hand, encoding looks like padding looks like this, then every zero I see, I throw away as a padding. And I stop throwing away stuff only when I encounter the first one, and then I stop throwing away stuff, right? So this is a great encoding. It's unambiguous and it cannot create collisions. So two different messages are guaranteed to encode differently, which is a key issue for a MAC security. The only thing is that if your message does end at the message block barrier, then, well, what happens if this message contains a bunch of a 1 with a bunch of zeros? The decoder is going to eliminate all of them. So you cannot do this. So what do you have to do? Well, in this case, you just mark one more block, 1 followed with all zeros, which does not matter much if your messages are long, that you perform one more block cipher operation, right? Because Now your message effectively became 3 blocks instead of 2. So both CBC MAC or NMAC are going to process 3 times rather than twice. You might want to eliminate this in practice, therefore, to optimize for even for small message sizes. And this is indeed happens in standard design. So here is the CMAC, which is a NIST standard version of CBC MAC. It actually optimizes CBC MAC in at least 2 ways, or exactly 2 ways. It has no final encryption step. It turns out that you can, instead of running an extra encryption, a faster way to eliminate attacks which deal with, as you will see in the homework, what happens when you don't have the post encryption. So what happens is that you can take the output wire and pretend that it was an output of an intermediary wire, and not pretend, just use it to supplant some intermediary wire and create an attack on a message of different size. So remember, CBC, when on fixed size, was secure. So there were no attacks unless you could use a final output and use it in a message that is either shorter than the original one or longer. Exactly that kind of trickery, another way to stop it, rather than have this post processing of encryption, a simpler way is that in the last operation of the block cipher in the CBC chaining, I used some extra pad extra mask that is going to be the final XOR, will take not just this wire and the last block, but also this key as a secret shift. If do you remember the DES-X construction, right? So remember triple DES, just ran DES 3 times on 3 different keys in a chain. DES-X skipped this and used the first and the last key in a much faster way. It's just an XOR before on the input to the block cipher, and the third key was used as an output mask. That's the kind of it is exactly that kind of trick that moves from encrypted CBC MAC to CMAC. The final encryption round, like the third cipher in a DES, triple DES, is replaced by an input pad, by using this extra key as an input pad. And it's also guarantees security. The other thing is that if so, in a standard operation, when a message is padded 1 and a bunch of zeros, this key, this extra key, is called K1. And how do we avoid this dummy block where if my message ends exactly at the block size boundary, then in a standard way, I would have to run this with one more block. That is a stupid block because it only has 1 followed by all zeros. Well, if that happens, I just use a different key. So the pad I used in this case, where the message is not exactly ends with the boundary, is K1. But if message ends at the boundary of the block cipher, I use K2. And these are independent keys, K1 and K2. So CMAC basically, all these little practical issues are optimized in a CMAC. So the different forms of sort of overhead the encrypted CBC MAC has, which don't matter if the message is long, that you have one more. But if the message is short, why do you want to pay this extra cost? It's like, just because you cannot analyze the more efficient construction, well, analyze the most efficient construction and be done with it. And let's have something that is, truly optimal in practice. And does this cost to create these new keys? Not really. Again, these keys could be created, derived from really one of these keys is really a master key, and it's used to derive all the others. Here I wrote this, and I just don't remember that actually keys K1 and K2 can be derived from key K itself. I'm not sure that works, or whether the three of them have to be derived from the master key. So if your key varies, then yes, it will cost you to derive this key K1 and K2. So there's a hidden cost in if your key needs to be small and you don't have storage. So you're a tiny mobile device and the key changes often, so you cannot locally store its expansion. Then you will pay by having to compute these K1 and K2, right? But even that is, how do I implement a PRG? Well, with like 2 block ciphers, say in counter mode, right? This way is how I get K. So I pay 1 PRF for K1, 1 PRF for K2. If I can cache them, then basically the overhead is like this encrypted CBC block. And that one was for every message, while this one I just do per every key. So I must be no worse than encrypted CBC, and most of the time I'll be better if I can have at least like a tiny amount of space where I can cache K1 and K2. Okay, so good. So we have this CBC and NMAC. And one more efficiency concern that we had in case of encryption was that like a counter mode encryption is parallelizable, but all these constructions are sequential. So here is how you could actually do a parallel MAC. Here is the construction. It's written for 4 blocks, but it can be any number of blocks. So there's 2 block ciphers. There's F and a P. P actually, yes, let's think of P as a block cipher as well. So I use P in a counter mode to derive, let's say block size is N. So I mean message size is N. So I have N blocks. I use P in a counter mode to derive N different paths. If P is pseudorandom, if it's a PRF, all these paths are like random strings. So, but they're independent. They can be computed independently, right? Like for this block, I don't need to compute all of these. to be able to derive this value. I use this as a input pad. I XOR it. I use it to XOR the block. I put the block through a PRF, and I put all of these blocks into the same PRF. So just so this is like an electronic codebook mode now. Okay. And I finally have to combine them, because how can if a MAC is truly parallel, so there is no combination between some processing of, say, the left side and the right side, then that cannot be a secure MAC, right? If some value was created independently from the right one, then I can mix and match. Right? If the left and the right was processed independently, and L prime and R prime are processed independently, then I can take whatever output of process L with whatever output of process R prime, and that also should be a correct MAC, and that will be a forgery. So they have to be combined at some point. But in this parallel MAC, they are combined with the lightest possible operation, an XOR. So this means that, if one parallel processing node, let's say, computes 100 of these, and the next one computes 100 of the next, then the first computing block can locally XOR all these 100 outputs. The next processing block locally XORs 100 outputs, and all they have to do that is non-parallel is XOR the final results. And then there is, in a way, it's similar to both encrypted CBC MAC and NMAC. I do a final processing, but sort of uncharacteristically with the same key. And that is my tag. The parallel MAC also has a beautiful property that it is, how do I call this? That is updatable. Okay. So here is the security of a parallel MAC. It is a worst exact bound here. I have to multiply by a number of L's, blocks. I didn't have that in the other constructions. It is intuitively what you would expect, that because of the parallelism, there is no, some bad events that happen can be reused all over the place, right? Because there is no order between them, although there is some order imposed by these input pads. Nevertheless, the more flexibility there is in this hardware, the more there is gonna be combinatorial attacks. Okay, so you have some bigger bound in here, which just translates that you can use it on well, smaller number of, but the total number of blocks is still the same as in previous cases. The term is incremental. So PMAC has the property that if I compute a MAC on some message, let's say the message is my file system. So I MAC my current state of a file system. And let's say I make changes in one of the files. So here in extreme case, let's say just one block. Okay. So let's say it's not a whole file system, it's just a file, and I make changes in one block of this file. I can recompute the tag on the modified file without computing all these intermediate values. It is hard to see from the slide, okay, and but if you change M1 to the blue value, M prime, one, you can use this line to recompute this wire on the modified message. Because if you had this wire, then you have the keys K1. So you compute Fk prime inverse to get this wire. Then you see all these wires, 1, 2, 3, 4, let's say, they don't change except for this one. This is the only wire that's going to change by modifying the black blocks into a blue block. So this is how you're going to modify the final tag. You recompute this wire on the black block. You XOR this wire with this one to get the XOR of all the remaining wires, and you store it for a time as a constant. Then you recompute this wire using the blue block forward. You retrieve that constant, XOR this wire with it, gives you this wire, run this forward, and that's your new tag. See? So the only thing that I needed to know about 1, 2, 3, all these output wires for all the cells except from the cell that changes is the total XOR. That's the only thing of interest in here. So I don't have to recompute them individually. I can invert this to compute here. I can go forward to compute that. I XOR the two, and that's my XOR of all the remaining wires. So that's why it's updatable. The fact that it's parallel and it's updatable is connected, because the way all these outputs are combined is through this XOR gate, which is invertible, right? So it is not a coincidence that the parallel construction is also an invertible one. It can be incrementally updated easily. So I'll just maybe spend like 5 more minutes. Sorry, so to go over time limit, but just to guide you over one funny thing with that relates to a MAC. You know what? No, actually, why don't I put it? So it's you can read it up at the end of the slides, and I do want to come back to it at the next section, because it's a nice case where you can you ask a very theoretical question, kind of. So remember, we started this whole encryption story by first we had a one-time pad, which is a very clean, simple way that it works. It doesn't use any assumptions. It doesn't use any computationally secure computational assumptions. It works against any attacker, not just computationally bounded one. Well, but it has this terrible boundary, right? That the key has to be as long as the message. Basically, it's a one-time encryption. But if you only want to encrypt short things and you only want to do it once, that's it. One-time pad is good enough for you. Is there something like that for a MAC? Because you see, we showed you how to do how a bunch of MACs are constructed in practice. We created them using this computational building block, a PRF. And all these were very closely related to encryption, right? So CBC's MAC circuitry is actually the same circuitry as a CBC mode of encryption. And so now that we developed all these tools to show how to encrypt, we show, okay, you can reuse them and use them to authenticate. But what if you didn't have any of these tools and you wanted to scale down your task to like a one-time authentication and possibly authentication of short messages? Is there something like, can you do something much easier, much cheaper, not without PRFs, without PRGs, without really any cryptography, something like a one-time pad? And yes, there is something like this, and it's called universal hash. It has a nice, clean algebraic structure, little more complex than a one-time pad, but still not that complex. It's an evaluation of polynomials, and it doesn't require any assumptions. It is it's perfectly secure, but it's a one-time MAC, and yet surprisingly, that one-time MAC can actually get you another solution for macking, and that solution has some its efficiency benefits over everything that you've seen so far. So you ask a theoretical question and you get a very practically relevant answer. So you can read up on the slides, but I will come back to it on Wednesday. Okay. Do you have some questions to all this MAC story? Okay. All right. Okay. The slides are online, and so is the reading guide. So I'll see you. We'll continue on Wednesday. Take care, everyone.